Okay, we're on to the final chapter of Decision 2, which is called Decision Analysis. Appropriate decision. Decision maths, here it goes. So decision analysis is a way for us to organise our thoughts when making a series of lots of different decisions, all with different outcomes, to try and work out what decision should we make here. Now, they resemble probability trees or frequency trees and follow that same kind of logic of how you flow through them, but they are different in many ways and they shouldn't be treated as a probability or a frequency tree. Now, they've got these different shapes that go on in them, and they're quite fussy about the way that the shapes should be drawn. So anytime that we are about to make a decision, as in the person actually doing this thing is deciding between two things that doesn't have a probability associated with it, we use a box, and these are called decision nodes. And you'll notice that the decision node, you could draw the letter D inside it, and that back part of the D here would be straight along a part of that box that we've got. Now, anytime that there is a chance of something occurring, whether we're then sort of like rolling a dice, or there's a game that's being played, or we don't know the outcome of something, we use a circle, because a C looks like a circle, so we're going for a chance node. Now, this isn't why they were picked. This is my way of helping you to try and remember what shapes that we use here. And then all of the branches are going to end with a backwards triangle, which are called the end or the payoff nodes that we have. And to remember that they go as like a backward triangle, we have this flat part at the end, but I kind of think of it like this. You know, when we have the play button for something, the play button is saying, yeah, let's keep going. So because it's the end of something, it's the opposite way around. Instead of it facing to the right, it is going to face to the left. So at the end of every branch, we will draw these end or these payoff nodes, boxes for decisions, and circles for chance nodes that we've got. There's only two exercises, decision trees and utility. And of course, we will finish this off with some exam questions. Now, as usual, the best thing here is probably going to be to see an example. So I'm just going to talk you through some of the key ideas that we have for decision trees. Now, we are going to be expected to draw our own decision trees as well as being able to interpret them. But if we can draw them, then interpreting them is really easy here. So I'm just going to quickly give you a bit of a preview of what they might look like. They look sort of like this kind of thing, where we've got a decision here to either offer the game or don't offer the game. If you do offer the game, there's then a chance outcome of this thing or this thing happening, and you'll notice all of them end in these end nodes or these payoff nodes that we have here. So that's the kind of thing that we're going to be drawing. So after we have a chance node, which is the circle one that we had, we would write the probabilities on the branches. You'll see me do that in just a second. I didn't have it on that one I just showed. We then have something called the expected value of the decision, which is going to be written inside the chance node. And this is called the EMV, or the expected monetary value. It's because it's mostly about money, these questions. That's why we have the expected monetary value. And we obviously want this to be as big as possible. We want the expected value of whatever decision we're making to be very high. And that expected value kind of just follows like the logic of how you would expect to calculate that. You'll see what I mean in just a second. The payoff at the end node is just written next to it, just kind of written in this bit that we've got here. And when making decisions, we can actually cross off the branches we don't use with a double line. So when we first draw the tree, we don't cross any of them off. But when we're then being told to actually make a decision, we can cross off the branches that are not going to be used. And we can also complete the tree by writing the EMV in the first decision box once we've actually gone about doing all of that decisions, once we've actually gone about the decisions that have been made, okay? So like I said, the best way to do this is actually just to go ahead and draw an example to show you what might happen. So it says that James is trying to decide whether or not to play a game using two fair tetrahedral dice. Well, you know what I'm going to do? I'm actually going to start off and just say, well, there's one thing that's actually going to happen to begin with here, which is that a decision is being made. And so he's making this decision, so I'm going to put a box in there, and I'm going to say that there are two decisions that he can make when deciding to play the game. He can either choose to play the game or not to play the game. So if he's going to play the game, then we would say that this would be a letter P. And not playing the game, we can do this little squiggle in front of it for saying, don't play the game. And then we've got these two different options of what's going to happen next. Oh, it's two fair tetrahedral dice. That's a dice that's just got the numbers 1 to 4. It looks, a tetrahedral dice is just a dice. It's like a pyramid with a triangular base instead, so it's only got 4 sides. If he scores a total of 6 or more, then he wins £4. Otherwise, he loses £4. And we're going to just draw a decision tree to model his possible decisions and outcomes. Okay, well, if he doesn't play the game, we already know what the outcome is going to be. It's going to be this backwards triangle to say that it's the end node that we've got there. I don't want to have that filled in. And we can actually put what the value of that would be, the expected monetary, the end part of that we would have at this part that it would be. He's not playing the game, so nothing happens. It's just going to be a 0 there. Now, this top part is going to be if he plays the game. And we said that if he plays the game, there's going to be a chance of something happening, which is why I'm filling it in with this circle for a chance node. And the two things that can happen is that he can either score a total of 6 or more to win, or he can lose. So I'm going to draw this onto my diagram for my decision making. And I'm going to just label these two things. Now, we know that they're going to end with triangles because there's nothing more that can occur here. Luckily, GoodNotes does these triangles drawn for me, but you'll just have to draw them as neatly as you possibly can. And then these two outcomes are going to be, this 6 one is getting a total of 6 or more, and this one is getting less than 6. Now, I did say, after we have a chance node, we can write the probabilities written on the branches. So with two tetrahedral dice, we need to figure out what's the probability of getting a 6 or more. Well, I could do a little sample space if I wanted to. So I can either get 1, 2, 3, 4 on that dice, 1, 2, 3, 4 on that dice. There'll be 16 possible outcomes, and 6 or more would come from a 3 and a 3, a 3 and a 4, a 3 and a 2 and a 4 is a 6, a 4 and a 2 is a 6, a 3 and a 4 is a 7, and a 4 and a 4 is an 8. So out of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, obviously it's 4 by 4. We have got 1, 2, 3, 4, 5, 6 out of those 16 of getting a 6 or more. So the probability of getting a 6 or more is 6 out of 16, which is 3 out of 8. So I can label that on this part of the diagram, which means the probability of getting less than 6 is going to be 5/8. Obviously, that would be the remaining spaces here would all be less than 6. Now, let's actually think about what would be gained on these bits that we have here. Okay, so let's actually think about what we should write as these possible outcomes. This one had an outcome of 0. This would be if he chose to play the game. Now, if he chooses to play the game and he gets 6 or more, he wins £4. So I'm just going to put a 4 next to this part. If he chooses to play the game and he loses, he's going to lose £2, which obviously we will represent with a subtract 2 like this. And now I have drawn the decision with his possible decisions and outcomes that we've got at this point, but I'm going to want to kind of keep going and try and figure out what he should do and how he's going to play this. So I have drawn the decision tree, but I am going to want to fill in this value because I said that the expected value of the decision is written inside the chance node. This is called the expected monetary value. So if he chose to decide to play this game, we're going to figure out what he would win as his expected value. I'm going to write this down as the expected monetary value. Well, 3/8 of the time he would get £4. So 3/8 of the time he would gain 4, and 5/8 of the time he would lose £2. So on my calculator, I'm going to calculate. There's always these multiplications for these expected values. If you have done any statistics, you'll kind of know this idea. So that's 3/8 times 4 minus 5/8 times 2. And we get that it is a quarter, or 0.25. We tend to do decimals for this because it seems to be like that's kind of the meaning of things. So if he chooses to play the game, he's going to have an expected monetary value of 0.25 each time that he would play that game. And then we can now see that we've filled in all of the stuff that needs to be filled in, because we can see from this decision point, he can either make this decision to play, which is worth 0.25, or he can make a decision not to play, which isn't going to be worth anything for this part. And so for part B, it does say to determine whether James should play the game and state his EMV. I'm going to say, yes, he should, as the EMV is positive and is 0.25. It's 25p is how much he could expect to win. So he should choose to play the game. And we can finish off by doing this last part. We can complete the tree by writing the EMV in the first decision box to show what's going to happen. So we're actually now saying this is what the expected monetary value would be, 0.25. And I'm going to say cross this one off with 2 lines because he is not going to select this option. He is always going to pick this one. Now, this is probably true if he was going to play the game hundreds and hundreds of times, every time he should pick to play the game. Because if he played it 100 times, he would expect to win £25. 0.25 times 100 is £25. But if he only wants to play it once, it depends on how risk averse he is. He might not want to lose £2. He might not have much money and really wants to hang on to those £2 that he's somehow got in his savings or whatever. And so when we get to the second exercise, we will look at about whether a game is worth playing, depending on how risky you are. So when we get to exercise 8B, which is this part, we will be talking about utility. And that utility is going to be different values to different people, depending on how risk averse they might be. So there's that first example of drawing a decision tree. We're going to do a more complicated now example of drawing a decision tree. And each time there's a decision to make, we're going to draw something. So Jess is playing £2 to play a game. She rolls 2 dice, and if they both show the same score, she wins £5. Otherwise, she loses. And so she doesn't have to play the game in the first place, does she? So I actually think we should probably go in with the first decision that is going to be made here. And the first decision that is going to be made is, should she even play the game? So let's zoom in on this. She's got 2 options. She can either play it or not play it. So I'm going to say that she's going to play it or not play the game. Now, if she doesn't play the game, nothing's going to happen. The game is over. Nothing is going to happen. So I'm just going to fill this in, and I'm going to say that this is a 0 that we've got here. Now, if she does choose to play the game, we know that there is some chance that is going to be involved, so I'm going to draw a circle for this. Please note the fact she is paying to play this game. In our previous one, James didn't have to play it. He was either just going to win or lose money. In this case, she is having to pay to play, and we'll have to incorporate that into the different things that we've got here. So to play this game, she rolls 2 dice, and if they both show the same score, she wins £5. So the options are now going to be from here and here. We're going to end up with the next parts of the branches. If they show the same score, she wins £5. So actually, if this is going to be my showing the same score branch, I can actually finish it with an end node like this. And I know that if they're showing the same score, she wins £5, but she had to pay £2 to play, which means that it's actually only going to be worth £3 to her because she's obviously gained 5, but she's lost 2. And I'm just going to jot down that this is the part where they have the same score. Now, you can work out the probability that 2 dice have the same score. It's pretty obvious that it's going to be a 6th, okay? If you imagine like a 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, there are 1, 2, 3, 4, 5, 6 where they have the same score, and 6 out of 36 is 1 out of 6. There's loads of other ways of thinking about that as well, but the probability they will have the same score is a 6th, and you will need to be able to do some of these bits of working them out. So the next thing is going to be if they have a different score, which is going to be a probability of 5/6. Notice how I'm not even reading the whole question. I'm just wanting to get information down onto the page as soon as she can. Now, if she loses down at this point, there's going to be some other things that happen. If it was the end of the game, I would draw a triangle and I would just say, if it's a different score, she has lost 2. However, there's more. If she loses, she can pay a further £1 to roll a 3rd dice. So she's got another decision to make here. Now, because she has another decision, I need a rectangle kind of shape. Doesn't matter if it's a rectangle or a square, just as long as it's this kind of shape that we've got. So she's got a decision to make. She can pay a further £1 to roll a 3rd dice. If the score on the 3rd dice matches the score on either of the first 2 dice, she wins £6. Otherwise, she loses. Okay, so we're going to have now 2 outcomes from this decision. She is either going to be allowed to decide whether she wants to play the game. So this is to play again. I'm not going to use the letter P because I've already used it earlier on. So I'm going to say that she can either play again, in which case there is a chance that something could occur, or she can choose not to play, in which case that's game over for her that we've got here. Now, if she's chosen not to play again, let's think about what would happen. Don't play again, I should write. Now, we talked about this. This would be when she started off. She's paid £2. She hasn't won anything and she's not played again. So she's lost £2 at this particular point. Okay, that's the end of that bit and we want to label what has happened there. But if she does choose to play again, she's going to have a chance of winning. It has to be the score on the third dice matching the score on either of the first two dice that we've got here. So we need to figure out what would be the probability of it being the same thing on one of the previous two dice. Well, let's just quickly draw out this tree that we've got here so that we've got those two outcomes. We're going to have it with some end nodes like this. Whoops. And so this is if it does show a matching with the third dice. So this is if the third dice matches, and this is if it does not match. So if the third dice matches, well, there's two other numbers that have come up before, and so there's probably a 2 in 6 chance of that occurring. You could do a little bit more explanation of where this is coming from, but the probability of two dice landing on the same value is a sixth. So if it's only the third dice, it's only rolled if the first two are different values, okay? So it's either going to match one of those two values that we've got, because if they did show the same score, then they would already be the same number and they would have already won. So they're showing different scores at this point. Maybe they've rolled like a 2 and a 3. So the probability of the third dice matching, it has to match one of these two different scores, which is 2 out of 6 or a probability of 1 out of 3. The probability that they don't match will therefore be 2 out of 3. And we'd be very, very careful about these last parts of deciding whether what money is going to be done here. So she's played the game and paid £2. She's played again and paid £1. So she's paid £3 to do this, but she's going to win £6. And £6 take away £3 is £3. And if she's in this very unlucky situation here, she's played for £2, she's played again for £1, and she's won nothing at all. So she's actually lost £3 in both of those cases. So now what we're going to do is we will add our EMVs to the chance nodes that we've got here. Now those EMVs are always calculated by doing this one multiplied by this and this one multiplied by this to get that value. So that is going to be a 3 times a third minus a 3 times 2/3. And obviously we add them, but because that one's a negative. So that is a 3/3 minus 6/3. That is a -1 that we've got here. So that one is a -1. But the choice that we've got between these two is a -1 and a -2. So out of those decisions, if she was going to make a decision between these two things, we're going to put in the better value, which is going to be -1. That is a higher value. So those were those calculations. Now, if I was going to do the EMV for this calculation over here, I'm going to be using different numbers. I'm going to be using the 3 and the 6th, and this -1 and this 5/6, because this -1 was the better choice out of the -1 and the -2, only losing £1 rather than losing 2. So this was the expected monetary value for this part. And now the expected monetary value for this part is going to be the 3 times the 6th minus the 1 times 5/6. So that is 3/6 minus 5/6, which is, have I done that right? 3/6 minus 5/6 is minus 2/6. Minus 2/6, which is -1/3. And like I said, we usually put these kinds of things in as decimals that we would have here. So I'm going to just cancel. I'm just going to write this as a -0.33. If you wrote it as a fraction, it would be fine to kind of have that in there as well. Okay. So we only can make the choices by crossing things that come out of decision nodes. We never want to cross things out of chance nodes because they're things that could happen. We can only make decisions and decide which things we will cross out. So it looks like the choices are between the 0.33 or the 0. So I think the best outcome in this case is unfortunately just going to be just don't play the game at all. So I'm going to advise that on the diagram. I'm going to say don't play the game. However, if she did choose to play the game, when we get to the next decision, then she should actually choose to play again. She should not just give up at that point because there is a better chance of winning something. So I can indicate that on the diagram that we've got here. So when it says find the best strategy for Jess as indicated by the decision tree, I'm going to want to answer that whole thing. The best strategy is not to play. But if she did and lost at first, she should play again. She should play again. And I've indicated that on the diagram with this bit being crossed out. So if she does play, she should actually play again here. And so I guess I should say why this is to be done. And this is because £0 is better than minus 0.33. And if she did, the reason that she should choose to play again is because -1 is better than -2 in this case. So that's everything that you need to know for exercise 8A. You've got to be pretty good at probability for this. You probably weren't expecting to do any probability in decision, but here we are, and it's these weird variations of, they're kind of like probability trees, but they're not probability trees. Definitely get used to the fact, anytime it's a decision, there's not going to be probabilities. If there's a chance of something happening, include them. Often people just want to do just the probabilities and forgetting to add in these branches where there's a decision that has to be made. So definitely go and have a work through exercise 8A. There is an additional example, which is example 4 about studying for mechanics and statistics, but I didn't think there was a ton to gain through going through that one. I thought they were quite simplistic. Okay, I will see you in the next video where we talk about the concept of utility.